So good afternoon, or it's still morning, everybody. It's my sincere pleasure to introduce Xudong's son. He comes across the pond from Maui, as they say. So Xudong joined us and joined the IfA in 2017, about 5 years ago. He received his bachelor's from the University of Science and Technology in China in Earth and Space Sciences. He received his PhD from Stanford University. He's a recipient of the prestigious UH Board of Regents Award for Excellence in Research, and he also is a recipient of the NSF Career Award. So he's been at the forefront of the research in solar physics, and he's recognized in the community for his work. He has a very interesting and tantalizing title, The Missing Stellar CME Conundrum, Lessons from the Sun. Okay, Xudong.
All right, it's a great pleasure to be here. Thank you, Shadia, for the nice introduction. The last time I was standing here, I was giving my job talk interview. So it's a very different circumstance. And
obviously successful, right?
last time I was wearing a tie, actually. Now I'm wearing upgrade. So okay, so this is I'm going to tell you about what I have been working on mostly for the past year and a half. So it's my new venture into the dark side, as you say, as people say, trying to connect what I used to do, or I'm still doing, solar astronomy to the stellar physics. And here's the outline of my talk. First, I will introduce to you this so-called missing stellar CME conundrum. And by CME, I mean coronal mass ejection, which is the large-scale ejection of magnetized plasma. And on the right-hand side is one of the earliest coronal mass ejection images taken by the at the HAO, High Altitude Observatory. And this looks like a slinky, and it outlines the twisted magnetic field they're in. And this is taken in H alpha. And this was nicknamed the Granddaddy CME because it's really, really huge. Okay, so after the introduction, I'll talk about what we have learned from the sun about what we can apply to the stellar CMEs. And in particular, I will introduce this concept of field eruption. Okay. And then I will talk about our contribution to this topic. Specifically, we propose that the suppression of the torus instability, is an ideal plasma instability that is believed to drive a significant portion of solar CMEs. So we believe that for more active stars, this instability is suppressed. And finally, I will talk about what we will do next. And this was actually written in NSF Astronomy grant proposal just submitted yesterday. So it's just in time for this talk. Okay, so before I start, I would like to give a shout out. On the left is my wonderful group members. They are doing very nice work on a variety of topics, especially Kai is working on stellar flare using solar analysis techniques. And on the right are my accomplices of this particular topic. All of them are actually, except for Jen, I guess, are solar physicists. Now we're trying to, apply what we learned from the sun in the stellar context. And on the lower right, Sumir Ranjan, he just defended his PhD last week, and he will be joining IfA early next year. And some of the work in the proposal is what he will be doing next. All right, first a brief introduction of what we call solar flares and CMEs. And I want to emphasize that it is fundamentally a magnetic phenomena. So it is driven by the magnetic field in the solar corona that dominates over the plasma pressure. Now, on the right-hand side is a cartoon. Solar physicists like cartoons, okay? They like to draw things because the real things are too complicated. In this cartoon, okay, all these lines, you can think of them as the magnetic field lines, and they are rooted in this bottom layer, which is the dense photosphere and chromosphere, okay? The density drops quickly in the corona where the magnetic field dominates. So you can see these magnetic field lines actually supports this circular structure. And in 3D, if you can extend this in the third dimension, you can think of that as a twisted structure, okay? And we call this the magnetic flux rope, okay, or MFR for short. And this is at the heart of almost all, actually all solar coronal mass ejections. We believe that is the essential part, okay? And what happens is that for these closed magnetic field lines, the convection and shearing motion in the photosphere would actually move the foot points of these magnetic fields around. And during that process, it would inject energy and magnetic helicity to this corona, and then it will create these twisted structure. Okay, so there's a lot of excess magnetic energy stored in these twisted structure. And this is exactly the energy that powers these explosive events. So when there's enough energy stored in the corona, at some point it will become unstable, okay? And this top part will lift up, okay, and becomes the coronal mass ejections. So when we talk about coronal mass ejection, we're actually talking about the magnetic field bringing the plasma along with it and escapes the gravitational well of the sun. So this part is the CME, okay? And now, in order for this part to escape, you need to disconnect the field lines from the sun. And what happens is that there will be intense magnetic reconnection occurring somewhere here, okay? So this reconnection is where the energy will be released. And that will power energetic particles, both upward and downward. So it will shoot jets of particles. And those that is being shot downward will hit the lower atmosphere, which is very dense and gets thermalized and creates intense emission. And that is what we call flare. So flare is the emission caused by this thermalization of the energetic particles. Okay. So as you can see, this is an intimately coupled system. Okay, so the current consensus is that CME and flares are two aspects of the same physical process. Okay. Now the thing is that one can occur with other. Okay, there is some possibly observational bias, but on the sun we sometimes can see one occurring without the other. So how do we know there are flux ropes? Okay, for the sun we have cute movies, very detailed. Okay, so this is a coronagraph that with a counter that blocking the sun. So the solar disk is somewhere here. Okay, now if you block the sun, then you can see these white light structures of the ejected plasma. You can see these untwisting motions very clearly. Okay. Now, flares and CMEs on the sun, if you think broadly, you would expect them to be occurring on other stars that are dominated by magnetic field as well, in particular these late type stars. And in studying these solar eruptions in detail, they can tell us something, for example, about the fundamental plasma physics, including how magnetic reconnection works, how particle acceleration works. Also, it would inform us about some stellar astrophysics topics. For example, in this particular eruption, you see these plasma being ejected, and then some of them actually fall back down, and that would mimic the accretion process in on other stars. Okay, and of course, the stellar wind and the loss of these material from CMEs will bring away the angular momentum that will cause stars to spin down. And finally, all these eruptions and emissions will have significant impact for planets, especially those that are very close in, right? So that has implications on exoplanet habitability as well. Now let's take a look at observational studies of flares and CME on cool stars or late type stars. What I mean specifically here are GK M dwarfs on the main sequence. I would not consider protostars. So optical surveys such as Kepler, okay, and TESS have found thousands of superflares on these stars with their bolometric energy on the order of 10 to the 34 to 10 to the 36 ergs. Okay, so we call them superflares because they are huge compared to the solar counterparts. On the right-hand side is one of the earliest papers on Kepler superflares, and these are the light curves. See, these large long-term modulations are caused by the star spots, okay? But then on top of it, you see these very sharp spikes. And if you zoom in, you see an exponential rise and a gradual decay. And the numbers here are the relative brightness compared to the average star brightness. Because it reaches about 1%, and in this case, 8%. That is very, very extreme, okay? By looking at the statistics of these flares, we see that they are very similar to the solar flare statistics, okay? So we think they are likely caused by the same physics, magnetic reconnection and plasma instability. And we think that they are also magnetically driven. For one thing, their corona is a low plasma beta environment. The magnetic field should dominate over the gas dynamics. And there's also empirical evidence for that. For example, we see stronger and more frequent flares on stars that rotate faster, have large spots and stronger magnetic fields. Okay. Now, if you compare these stellar flares to what we see on the sun, these are the light curves, total solar irradiance, okay? So this is one of the largest flares, X4 class flares, and the red curve is in soft X-ray bands. You see a very clear rise and decay. But if you look at the total solar irradiance, basically you don't see much, okay? There's basically nothing here. Only when you do this so-called super epoch analysis, where you stack hundreds of large flares on top of each other and get rid of the noise, that you can see that these largest solar flares has a total solar irradiance variations of about 20 parts per million. So it's tiny compared to the 1 or several % of the stellar flares. Okay. Now, what about CME? And here's the interesting part, okay? CME detection is quite difficult for other stars. For the sun, we can see this in, time sequence of imaging observations. For other stars, you don't have that kind of luxury. So you will have to rely on more difficult spectral observations. And high resolution spectral monitoring is expensive. You can't do that all the time, right? So you don't necessarily catch one. So up to now, detections are relatively rare. So only about 40 candidates have been observed through a variety of techniques, such as Doppler shifts and Balmer lines, X-ray absorption, or EUV or X-ray dimming. So if we have time, we can go into the details later, but I will skip that for now just show you one very nice example that was published last year. Okay. So here is I guess it's called river plots in stellar physics. So what is plotted here is H alpha spectra. And on the x-axis is time, and y-axis is the wavelength. So each column of data is one spectra. And this has the pre-flare, pre-eruption spectra subtracted. So you're only seeing the variation, okay? Now, the red color here, this is not redshift. The red color shows you emission, and blue color shows you absorption, okay? And the wavelength indicates the redshift or blue shift. So if you are below this line, the fiducial line center, this blob down below this line is a redshift component. It's in the longer wavelength. So at the beginning of this event, you see redshifted emission, okay? And then immediately that is followed by a large Doppler blue shifted absorption component. And that blue shifted absorption component, the velocity gradually decreases, okay? So the interpretation from this author is that you have a CME erupting towards the observer. Okay, so at the beginning, what you see is the flare component. That is the downward injection of the particles. You see the emission of the flare, and you see a slight blue redshift. Now, after that, what you see is the absorption of the H alpha emission by this dense, heavy blob of material that is moving towards you. So that is why you see these fast blue shift with a speed of about 500 kilometers per second. And that is typical for a solar CME. But what happens is that it gets slowed down either by magnetic Lorentz force or the gravity. So it sort of gets slowed down and fall back, actually eventually fall back because it becomes redshifted after a while, right? So the authors interpreted this as a detection of stellar CME ejecting outward, then slow down and eventually fall back. So these kind of high resolution observations, you need to monitor this with a cadence of several minutes, but at the same time, you also need enough signal to noise, and that is very difficult, okay. Anyways, this is all the candidates that we have, about 40, and that is very few compared to the thousands of flares we have seen. Now, because this has...
So you don't see this in the white light curve at all? Do they have one?
Just white light.
It's just a normal optical light curve. Like who would Kepler see if that would go off on the star?
Oh, yes, because the corona is a billion times dimmer than the disk, and even with the CME, the higher density, if you look at the coronagraph, okay, for the sun, the CME brightness is very, very small. So there's basically impossible to detect these things.
Okay. The flare emission.
Flares, yes. Yeah, flares. That's all the flares that we see here. That's huge, right? Okay, so because this has garnered enough interest, people have been devoting resources in monitor these things. They have spent tens of hours coordinate observations with both optical imaging and radio monitoring. So one signature of these CMEs is that if they move supersonically or super aphenically, they will drive a shock in the front, and that will give you a so-called type 2 radio burst with a signature drift in the frequency. Okay, so this is the hallmark of CME for solar CMEs. So people have been doing optical plus radio monitoring for tens of hours for the nearby flaring M dwarfs. Now they have caught several super flares during that process, but none of the radio signature at all. So the current conclusion is that there is perhaps, there are perhaps very few CMEs, and this is not an observational bias. Now, so this is what I call a missing stellar CME conundrum, especially in comparison with the solar eruption. Okay, so on the right-hand side is the CME association rate with a flare. Okay, so you count the number of flares and you count how many of them are associated with a CME, and you plot them in this histogram as a function of the energy of the flare. So what this shows is that as the flare ramps up in energy, there's more and more likely to be associated with CME on the sun. Okay, so for large flares, it's almost 100%. Now, if you compare that with the stellar observations, apparently we have too few stellar CMEs, okay, based on the solar scaling. So this comes as a surprise because all the other statistics of the stellar eruptions follow the solar scaling law, but this one just deviates so much. And there's another factor is that for those that have been detected, when you have a velocity estimate, we found that the detected CME velocity is quite low compared to the solar scaling. I won't go into details, but this is the second manifestation of the missing stellar CMEs conundrum. So even those that make out of the stellar gravity, they are quite slow. Okay. So there are a few possibilities to address this conundrum. Now you can think of that as observational bias, but I think it is quite unlikely given the recent intense monitoring. Okay, it's possible that the eruption is due to a different kind of physics, but that is also unlikely given what we know about their environment. And what I think is the most possible explanation is that there these stars, okay, these stars, flaring stars, active stars, have a different magnetic field environment compared to our sun. Okay, because these events are all magnetically driven. So if there's anything in their different behavior, it's probably due to their different magnetic field. And that looks reasonable. That's possible if you really plot the stellar magnetic field. In this case, it is approximated by the relative X-ray luminosity. Okay. This is a good proxy of the stellar magnetic field. According to the star's Rossby number, which is basically a measurement of how important their rotation is compared to their convection motion. So the faster a star rotates, the smaller their Rossby number is, and usually they have a stronger magnetic field. So this is indicated by this power law. Okay, as the stars spins faster and faster, their X-ray luminosity or magnetic field becomes stronger until it reaches this critical point of 0.1, then it saturates. Okay. Now, here the red dots indicates fully convective stars. So it doesn't really matter if it's a fully convective or a partially convective stars. All of them seems to follow the same scaling law. And if you plot the sun here, it's way down here, okay, with a X-ray relative luminosity of about 1 in a million compared to the total luminosity, and a Rossby number of 1 to 2. Okay, so the sun is actually relatively inactive with a relatively weak magnetic field. So it is possible that for all the active stars we measure up here, they behave somewhat differently compared to the sun. Okay. So what is the difference? So in order to answer that, let's take a more detailed look about what we can learn from solar CMEs. Okay. So this is a huge topic that I won't be able to go into, but in the spirit of a solar physicist, I plot cartoons here. So these are the three main classes of solar CME driving theories. We call them torus instability, magnetic field breakout, and tether cutting. Okay, again, I won't go into details, but what I want to emphasize are two things here. Okay, first of all of them need to contain a flux rope at the heart of the system. Okay, so for torus instability and tether cutting, you have a flux rope at the start of the eruption. And for this particular magnetic breakout scenario, the flux rope is generated during the eruption, but that doesn't really matter. Okay. And the second, and I think is more important point, is that in order for the eruption to proceed, there is always a balance that you will need to break. And that is the balance between the expanding magnetic flux rope, that is the core, and this overlying background magnetic field that acts to confine the flux rope. So before eruption, these two are at a balance. The flux rope wants to get out, and the overlying magnetic field keeps it in. Okay, so it's a balance of their Lorentz force. And during the eruption, this balance is broken, and the magnetic flux rope will just erupts. So for the solar CME, whether CME actually successfully erupts depends on the balance of these two. If the confining magnetic field back in the background is too strong, then the CME cannot proceed. Okay, so this is the point that I want to emphasize here. So on the sun, we do see these interesting events called field eruptions. Okay, for most of CMEs, it starts out slow, but then it has exponential, acceleration. There is a type of event called field eruption. Let me play this movie in EUV. Okay. So what we see here is a very dense blob of material seems to shoot up, and then as it shoots up, it writhes and kinks, and then it seems to run into a wall, then it drains down. Okay, so for this event, there's no CME at all. So this is what we call a failed eruption. The beginning of this event is very similar to the successful CMEs, but then at some point, the magnetic flux rope just cannot escape. And that is because of the strong background magnetic field confining this event. Okay. Now, another point is that although the CME doesn't make out, there is still lots of reconnection down here. So you see intense flare emission. So this gives you flare, but no CME. So this particular kind of, field eruption. Okay. So this happens to be one of my own work in 2015, and this particular active region on the right-hand side. So for solar active regions, we give each one a number to identify them. So this one, 12192, that appeared in October 2014, was the largest sunspot group since 1990. So they're huge. Okay, as you can see, this bipolar region. It is also the most flare productive active region of the last solar cycle. However, if you recall, the association rate of large flares with CMEs on the sun is almost 100%. But for this event, for this active region, it is an extreme outlier in the sense that none of its large flares is associated with the CME. Okay, so this guy is a black swan. I think whenever you see something this extraordinary, you probably can learn something. Okay. So what we went in and looked at their magnetic field properties. In particular, we compared this big guy without CME to two much smaller guys. They are also flare productive, but all of their flares were accompanied by CME. So if you compare these two, if you compare the magnetic flux rope, which is approximated by the properties of the magnetic field in the center of this active region. Okay, so if you look at the properties at the center of this active region, well, we concluded that this big guy without any CME has less energetic magnetic flux rope. And at the same time, if you compare their overlying or background magnetic field that is approximated by the total magnetic flux in this active region, so this one's huge. It has lots of magnetic flux, right? So this guy has a stronger background magnetic field compared to these two guys. Okay. So we concluded that the reason of this active region not producing any CME is a combination of a less energetic MFR that cannot come out and also a strong confinement due to their background magnetic field. So this is what we learned from this particular active region. This active region actually caught the eye of several stellar astronomers, including Jeremy Drake and Rachel Austin, who have been studying the missing stellar CME Conundrum. So in one of their conference proceedings, they quoted this active region as a solar analog of the stellar CME-less flares. And they cited my paper, and that is how I got into this question. So that's by coincidence, but I think it's an interesting story of reading papers from other related field can get you into interesting new directions. So what I was just talked about is basically represented in this MHD model where you have this overlying magnetic field in orange and the magnetic flux rope in blue. And the magnetic flux rope tries to get out, but the overlying field, the cage is really strong, so it suffocates this eruption. Okay, so this is the basic idea. I think that can also be applied to the stellar cases. And now, more recently, we actually found more evidences on the sun. So one very significant evidence is from one of my collaborators who surveyed all the large solar flares for the past several solar cycles and compared that with the magnetic flux, which is a proxy of this orange overlying field. What she found was that all the extremely large solar active regions with magnetic flux larger than 10 to the 23. So this is sort of the very large number in terms of solar active regions. So as soon as this active region hits this this threshold, they still produce a huge number of intense flares, but none of them actually is associated with CME. Okay, that is a still small number because these active regions are rare. But once you have these monster active regions, all of their flares are CME-less. So this is in support of the confinement effect of this overlying magnetic field. Now, so Julian Alvarado Gomez, who worked with Jeremy Drake in CFA, he was the first one to apply the solar MHD code for CMEs in the stellar regime. So he studied a few cases using stellar perimeters and showed that when you have a strong global magnetic field, indeed, it can suffocate these CMEs. All right, so there's some numerical evidence for this as well. Okay, so that's what we learned from the solar studies. Okay, now here's from now on, I will briefly present our contribution to this topic. So what we did last year is that we took one of the leading theories of solar CME, which is the torus instability, and we argued that the suppression of this torus instability on more active late type stars contributes to the lack of CME detection. So that's our argument. Now, this torus instability is basically expanding instability of a toroidal magnetic flux rope. So you have a half circular magnetic flux rope, and the Lorentz force in this flux rope will drive the CME to erupt. And that is suppressed by the overlying magnetic field. Okay, so in this torus instability theory. Now, this instability will kick in if, okay, so this is the instability criteria, is that when the background magnetic field that confines the magnetic flux rope decreases with height fast enough. So if you have a strong background magnetic field in the low corona, but it decreases really rapidly, then this instability will kick in. And this is quantified by this so-called decay index, this free perimeter, okay? And that is basically, if you approximate the background magnetic field as a function of height, if you measure its slope or the power law index, if it's smaller than 1.5, which means the magnetic field decreases with height very, very slowly, okay? When you have a small decay index, this instability will not start. Okay, so you won't get a CME. And oppositely, if the decay index is large, that means your background magnetic field decreases with height very rapidly, then you will get this torus instability. Okay. Now there's a accompanying concept, which is the critical height. The critical height, HC here, is basically the height at which your decay index hits this threshold. Okay. And in the corona, because the decay index increases with height, so in the lower corona, from this critical height below to the surface, this is what we call a so-called torus stable zone. So if your magnetic flux rope lives here, it won't erupt. But for some reason, if your magnetic field grows and hits above this boundary, then the torus instability will kick in and make it erupt. Okay. So this concept is illustrated by, on the right-hand side, by two contrasting MHD simulations. So in the first one, the background magnetic field has a relatively low torus, the critical height, somewhere around here. Okay. So as the magnetic flux rope starts to increase in height due to slow reconnection, okay, once it hits this height, it erupts. Okay. And in comparison, this particular event, this particular simulation has a very large critical height. So although you have reconnection here that drives up the magnetic flux rope, it never hits this threshold. Okay, so there's no CME. Okay. So what we're looking here really is the critical height, okay, where the this instability would kick in. So if you apply to the stellar context, okay, we argued that the field eruption caused by the suppression of torus instability can simultaneously explain flare emission and lack of CME detection. And when you have a very large torus stable zone, okay, there are two things that can happen. So in the first case, when you have a very large critical height or extended torus stable zone, TSZ here, in this large torus stable zone, the flux rope can start erupting, okay, triggered by some other mechanism, okay, for example, kink instability. But once it starts to erupt, okay, then the suppression of the overlying magnetic field will kick in and stop the eruption from proceeding. So this is, I think, what explains this event that I just showed you, this upward eruption, okay, then that gets stopped somewhere in the middle. And one of my collaborators was actually simulate this event using a strong background magnetic field and kink instability. So this is the first mode. If you have a large torus stable zone, flux rope eruption cannot proceed. And there's a second mode. Okay. In the second mode, there can be two different torus stable zones. I will explain this in a minute. But what really happens is you have a torus stable zone in the low corona, and once your flux flow breaks through this top layer, it can erupt. But then there's this peculiar magnetic environment where you have a secondary torus stable zone on top that acts as a second wall that confines this eruption. Okay, so I'll explain that in a minute. But what I'm trying to say here is that once you have this extended torus stable zone, eruption is very difficult to proceed. Now, this seems very abstract, but what we're trying to do really is to use the stellar perimeters and put a number on it to see how big this torus stable zone is. And to this end, we utilize a very idealized magnetic field models. Okay, that is, we use a very simple coronal magnetic field model called potential field source surface model that assumes that there's no electric current in the corona. To explore the basic ingredients of the stellar magnetic field, we only include two components. So this is a grossly simplified picture. We only include one pair of star spots as a dipole here, and we only include a global dipole component. Okay, so we want to see the different relative strength of these two components. How would that change the magnetic environment? So for simplicity, we put the spots symmetric across the equator. Of course, this doesn't really happen in reality. And we make that align with the global dipole. And because these two fields are aligned, that gives you a maximum confinement. Okay. Now, what we're trying to do here is we actually vary the relevant free perimeters to see their effect on these so-called torus stable zone. And the three relevant free perimeters here are the star spot size, how big the star spots are, okay, and how strong the global magnetic field is. And there's a third parameter called source surface height, which controls how open the magnetic flux is. So here, some of the magnetic flux are closed. Okay, this is the part that actually is providing the confinement. And some of the magnetic field are open into the atmosphere, the magnetosphere of the stars. Okay, so the third parameter controls how much magnetic flux is opened. So as we vary these three parameters, we systematically calculate the decay index and the critical height and see how that changes. Okay. Now, these three free parameters gives you a huge perimeter space, and we want to put some constraint on that from observations. And for the first parameter of the star spots, okay, we have some observational constraints. And we know that for these more active stars, the star spots are generally larger compared to the sun. Okay, so on the right-hand side, here's another cartoon of a solar physicist that illustrates that in order to produce a flare of these energy, 10 to the 32 up to 10 to the 36, how big your star spot must be. Okay, so for the sun, the typical energy is 10 to the 32, and that is the typical sunspot size. Now, for a super flare on a cool star of 10 to the 36 erg of energy, you really need a huge star spots. Okay, and that could be a cluster of spots. It doesn't have to be very monolithic. But we do know that these large spots exist. And I actually put a quote here from a review article. So for large star spots, okay, the magnetic field is strong, so you can look deeper into the atmosphere. And the star spots would appear to be depressed into the stellar surface. And this is what we call Wilson depression. And now the star spots are so huge that would make the star look like the logo of a well-known computer company. So it will basically look like an apple with a bite lost because the Wilson depression would be so severe. Okay. Now the magnetic fields of these star spots, we can get that from the Zeeman-Brontning or Zeeman-Doppler imaging. I'll explain that in a minute. But the baseline is that the magnetic field in these star spots are similar to the sunspots, on the order of a few kilogauss. Okay, so we have some handle on the size and magnetic fields of these star spots. Now, for the large-scale magnetic field, there is this so-called Zeeman-Doppler imaging technique that measures the Stokes polarization profile as the star rotates. So if you apply this inversion technique And you can figure out from a sequence of modulated, rotationally modulated polarization signal of what the large scale magnetic field should look like on the stellar surface. Okay. So this technique will allow you to recover the large scale magnetic field, usually lower than spherical harmonics of 5. So it's really, really only the large scale magnetic field. Okay. And most importantly, it is insensitive to star spots. For one thing, it does, because star spots are dark, right? You don't give much photon. So really, the polarization signals here does not really include the information from star spots. Another thing is that because it's insensitive to small scale structures, whatever you have that is smaller than a few tenths of a degree, this particular technique cannot resolve it. So it's insensitive to star spots. Okay. But what we get out of this is that for M dwarfs, okay, many of them could have kilogauss dipole field comparable to the star spots magnetic field. Okay. Very, very strong magnetic field. And in comparison, the solar global magnetic field is only a few Gauss, okay, 10 at most. And finally, is this so-called source surface radius that controls the topology of the global magnetic field. And it has been argued that as the star ages, there will be more and more open magnetic field. And one can actually estimate what the number should be according to their effect on the stellar spin down or the angular momentum loss. So on the right-hand side is an experiment of the stellar angular momentum loss simulation from ab initio MHD. So on the x-axis are the stellar ages, and on the y-axis, on the top is the amount of open magnetic field. Okay. And then in the middle is the angular momentum loss. And in the bottom is the effective, the so-called source surface, this free perimeter. And the this particular evolution of angular momentum loss needs to be exactly like that to recover the Schumannish law. And in order to satisfy that, you will need to have this kind of evolution of the source surface radius. Okay.
What are the different colors?
Different colors are for stars with different rotational speed or magnetic field. Blue ones are more active. So what this says is that as the star ages, the topology changes. Basically, this is what it's saying. Okay. Anyways, all these observations give you a handle of what your free perimeters should be like. And now we come to the result of this simple model. Okay. So these are the basic results from our simple calculation. And I will show you a few of these kind of plots where in the x-axis, I'm showing you the decay index. Okay, this is the number that we're actually looking at. And the y-axis is the height above the stellar surface normalized by the stellar radius. So this is one stellar radius above the surface. And these curves shows you the change of the decay index as a function of height. So on the left-hand side, I'm showing you the results for dipole magnetic field only, okay? And when these curves hit the critical decay index 1.5 that I take here, this particular readout of the height gives you the critical height, okay? So as you can see, this particular result shows you that as the source surface radius increases, your critical height increases and can reach as high as 1 stellar radii. This is large compared to the solar case, and I'll show you in a minute. Okay. So this is for dipole magnetic field alone without any star spots. Now, if you have star spots alone, okay, these different colors shows you star spots of different sizes. Okay, so this light blue shows you star spots of about 5 degrees in size. That's the typical size of the sunspots. And this dark blue shows you 25 degrees, large star spots. And as you would expect, as the star spots becomes larger, the decay, the critical height increases as well. Okay, and these numbers are, you can see 0.1, 0.2 compared to the dipole alone, 0.6, 0.7. Okay, so for star spots, the critical heights are pretty low, and for sunspots especially. And as the spots gets larger and larger, the critical height increases. So as what this says is that as the spots gets larger, it is more difficult for the CME to erupt because the decay index increases. Okay. Now you can combine these two and it gets even more complicated. Okay, but what I'm trying to get is that on the right-hand side, I'm showing you the large star spots. Okay, we are only considering large stellar star spots. And different colors here shows you when you add different numbers of global dipole on top of it. So for these large star spots, this global dipole would increase the critical height by a little bit, but not much. Okay, it helps, but doesn't make a fundamental difference. The fundamental difference really comes in where you have these smaller sunspots. Okay, for these sunspots, when you don't have a global dipole, it looks like this. But once it starts to look at just a 10 Gauss global dipole or 100 Gauss global dipole, these curves start to look like crazy. Okay, so if you have 1,000 Gauss global dipole, the critical height is 0.5 or 0.6 stellar radii compared to 0.08 without a global dipole, right? And more interestingly, if you have some intermediate value of 100 Gauss, this curve curves back and hit the critical height 3 times. Okay, so that means somewhere below here is the first so-called torus stable zone where eruption cannot occur. But then you have a secondary. Okay, you have a secondary torus stable zone here, a second wall, if you can think. Okay, so if a flux probe starts to erupt somewhere here, it will hit the second wall. Okay, so this is second mode where you have a sunspot, but in intermediate global dipole. And this kind of behavior, we never see that on the sun because the solar dipole is only a few Gauss. Okay, so basically we are exploring a regime that we have never observed. This actually indicates, the star spots and global dipole would behave differently in controlling the eruption. The spots would provide a local scale confinement, whereas the global dipole would produce a global scale confinement, and their complex interaction would determine the final result. Now, if you plot everything in one plot, you can show this parameter space like this. Okay, in the x-axis is the spot size, in the y-axis is the dipole strength, and on the left-hand part, this is dominated by global dipole. On the right-hand side is dominated by spots. And the secondary torus stable zone I just talked to you about only happens in this very tiny corner, okay, where you have these relatively small spots and the intermediate dipole. And the typical solar perimeter regime is this tiny fraction, okay? So there's a huge perimeter space that is not explored, that we don't know what will happen. Okay, and for using this simple model, we showed that for these strong bipoles, the torus stable zone is huge. So the eruption is very unlikely to occur. So that's basically the conclusion. Now, of course, this study has lots of caveat. For one thing, it's only a first order estimate. Okay, in reality, the cases can be extremely complicated. I'm just showing you here a close-in view of DKIS observation of sunspots. You can see all kinds of fine structures and fragmented structures. It looks nothing like the huge monolithic spots that I just showed you, right? And also, this is the static model. Okay, there's no magnetic flux probe at all, and there's no dynamics. And finally, it does not consider other modes. For example, there are flares without a magnetic flux probe at all. Okay, so these are all the caveats. But nevertheless, I think this provides the first kind of, first order estimate, showing that on stars, the torus stable zone grows much bigger than what we see on the sun. And that should fundamentally change the eruption potential of coronal mass ejections. Now, finally, let me briefly talk about what we will do next. And these are the 3 parts of our proposal, basically. Okay. So one of our colleagues will look into, will use these idealized MHD models of solar eruptions, where you can prescribe these sunspots and flux probes analytically, and then let it evolve to see whether an eruption could occur. So these are simplified MHD, zero plasma beta, no pressure, whatever, or no thermodynamics. So you can run that basically within a few hours, okay, for each case. This will allow us to explore the perimeter space I just showed you very efficiently. And this time we will have full dynamics, okay. So we are going to run a grid of models to see whether our prediction from that simple model stands. So this is the first component. The second component is that we are going to use the most sophisticated solar CME eruptions and drive that with non-solar CME mechanism on realistic stellar magnetic fields. Okay, so this will be our last step, and we will probably going to run 1 or 2 cases eventually. Now the question is, how do we know what the stellar magnetic field looks like? Okay. Now I talked to you about the ZDI technique that can give you the large-scale magnetic field maps. So on top is, on the left-hand side is the solar magnetic field at 1 degree resolution. Now, if you forward model the Stokes perimeters and run through it with the ZDI technique, what you get is on the thing on the right. Okay. This is only a very lowest harmonic coefficients. And on the left, this is 1 degree and it's saturated at 100 Gauss. And on the right-hand side, the strongest field here is only a few Gauss. So you're losing lots of magnetic energy as well. So this is the kind of observational constraint we have. And this obviously cannot give you these complex dynamics. So what we are going to do in collaboration with Jen and another colleague, and this is the work that will be carried out by the incoming postdoc Sumya Ramshan, is that we will utilize this so-called surface flux transport model to forward model what the stellar surface should look like. Okay. To do so, okay, that is based on the fact that we know active region of the sun and presumably on stars, they follow known patterns and statistics. For example, the solar active region emergence follow this butterfly diagram. So at the beginning of a solar cycle, it emerges at higher latitudes, and as the cycle progresses, it moves down to the lower latitudes, right? We also know that their sizes follow the log normal distribution and etc. So once we know these kind of distributions, we can scale it to the stellar context and draw from this distribution a random ensemble of what the active region should look like. Okay. And then the detailed evolution of the magnetic flux on the stellar surface actually follows the simple magnetic, not simple, but follows this one equation, magnetic induction equation. And the surface field is a result from a dispersion of the active region magnetic flux by the surface flow, including the meridional flow, surface differential rotation, right, and the supergranular diffusion. So once an active region flux emerges on the stellar surface or solar surface, it just gets dispersed by these kind of flows. So this particular solar surface flux transport model emerge active region on the stellar surface, subject that through the dispersion processes, and it can well represent what we see on the sun. And it has also been used on the stellar cases and has successfully reproduced many stellar properties. So what we're going to do is we're going to run these kind of models, and these kind of models is very cheap, so we can run a huge ensemble of it. And we're going to sample the perimeter space very efficiently. And on the right-hand side is an example of a solar-like star and a more active stars with a smaller Rossby number. You can see the active region gets really, really cramped into each other. The structure is really complex. Okay, so we can run these suite of models and use that as the background for our MHD simulation. And there's a bonus to it. So once we have the magnetic field distribution, we can tell which part of the stellar surface is occupied by a dark spots, which part is occupied by faculae. Okay, then we can forward model the brightness modulation of the stars, and that will give you, for this proposal, thousands of years of light curves sampled at 30-minute cadence. And if you recall, that is the kind of data Zach used in his machine learning model to infer from test light curve, the rotation modulation of stars. And now we have a more physical model to produce these kind of light curves. That's one other goal of our proposal. Okay, that is all I want to talk. And oh no, one more thing. Okay, I forgot before I forget. DKIS can also help from the solar perspective. Okay. One thing DKIS can do is that it can give us multi-spectral line diagnostics. In this case, in the helium-1 1083 nanometer window, it also has so this is a chromospheric line. It also has a nearby photospheric line in silicon. Okay. So DKIS will give us simultaneous observations, spectral polarimetric observations in multiple lines that probes different heights. So effectively, we can probe, for example, if there's a magnetic flux rope, what the field should look like in this layer and at a higher layer. And if the magnetic field is actually twisting by sampling multiple heights, we can get a much better constraint of what their structure should look like, right? So this is about the magnetic flux rope. And then for the first time with DKIST, we can routinely observe the coronal magnetic field. And this will give you a diagnostics, for example, of the background magnetic field, how fast that evolves with height. Okay, we get a direct observation of that value instead of inferring from the surface structure. So this is the kind of new diagnostics DKIST can give us. Now, this is my summary. So what I'm trying to, the take-home message is, for stars, it acts differently. We have flares, but no CMEs. And we think that is fundamentally caused by a different magnetic field environment. And that's it. Thank you.
Exciting talk and research. Any questions? Mike, do you have? Oh, go ahead.
Can you go back to the summary parameter plot that shows which,
Oh, you passed it.
Yeah.
Which one are you?
From your recent paper that shows the 3 different parameters.
Okay,
Grid.
okay,
the grid.
here.
Seems, yeah, this one. So it seems to me like there's only a narrow parameter space that actually allows
True.
CMEs to be, right? Do I understand it correctly? So in the, the stable zones, both in the top left and in the red area, wouldn't allow CMEs to be driven in stars. Do I understand it correctly? And if the answer is yes, do we know for the stars that have been monitored and have the lack of CMEs, do we have an idea whether if they all fall into the right parameter space?
That's what we're going to find out with the new investigations. So this one is really a simple, first order estimate. And also, as you said, there's only a narrow range that CME could be allowed, and there's only a narrow range here that is realistic, because the spots size and the dipole are probably correlated, and we don't know what the correlation is, and that could be found out exactly by our surface flux transport model. Okay, so there might be only a small range that is allowed, and in that range, only a small portion, like our sun, allows frequent CMEs. For the rest, it would be more difficult. So I think the implication here can be profound in the sense that it would change, the stellar angular momentum loss if you don't ever have any CME, or the impact on their habitability, the planets.
Any other questions? Any questions from Zoom land?
Yeah, we have one from Esther.
Esther, go ahead. Are you muted, Esther? Okay. Maybe I can ask a question while she.
Okay, let me try it again. Okay, I was sorry. I went from unmuted to mute. So I was interested in the later slides where you were talking about how the DKIST observations of different diagnostic lines would allow you to probe to different heights in the atmosphere. And I'm curious about how large that extent is in terms of your attempts to figure out what is happening at different scale heights. You listed some of the lines, but I was kind of curious about your estimates of how well those diagnostic lines are going to probe the scale heights of interest for different phenomena.
That's a really great question. I'm not an expert in this, but the lines, okay, in order to probe the magnetic field, you should, this should be a line that we already understand pretty well. And most of these lines lie in a very narrow range, from the photosphere to the mid-chromosphere, I would say. So it's basically probing the very lowest layer, okay, very lowest layers of 1,000 to 2,000 kilometers. And this does not give you, that gives you a few scale heights. And what it's mostly useful is for these kind of low-lying magnetic flux ropes, okay? Most of the large eruptions are driven by these low-lying magnetic flux ropes in the active region, and their height is expected to be no more than a few megameters. So with these different lines, we're really sampling the lower half of these active regions, magnetic flux ropes. And if the twist of the magnetic flux rope is severe, even if we have a very small difference in their height, we should see the magnetic vectors changing orientation and strength significantly and systematically. And I think the most helpful thing will come from that. But no, it won't sample a large range of heights with these lines. What we can do with heights is basically the coronal magnetic field when we view the active region from the side. Okay, of course, this is if it involves optically thin lines, then it's an averaged magnetic field. But when it's on the limb, we are able to get at least the field vectors, for example, from the linear polarization, right? Of how it actually evolves with heights. And for that, we can probe a much larger heights from the solar surface to the limit of the field of view of Dicke's, which is about 1.1, 1.15, this kind of heights.
Sure. And of course, when I was phrasing my question, it was not so much that I thought you would get a really large range of different scale heights, but you probably have some feeling of how well different diagnostic lines probe what you feel are the key regions for your models, for your different models.
Yes.
And that was really what I was interested in.
Yes, yes. Yes, as I said, the well-known photospheric lines with only maybe 100 or 200 kilometers of different formation heights are good enough to give us a sense of the gradient of magnetic field. And that, for one thing, can give you the curl of the magnetic field, helps us better estimate the curl, which will give you the electric currents, right? And that is exactly where the non-potential magnetic field or the excess magnetic energy comes from.
Thank you.
Okay. Can I ask?
Yeah.
I have two questions. One is the detection of CMEs.
Yeah.
I mean, you know that the flares have been known for over centuries, but CMEs were only detected in white light in 1973 because they are so faint.
Yeah.
Now you have covered mostly focused on what you call flux ropes, I call prominences, in active regions, but there are many more prominences covering the whole solar surface.
Yeah.
So that's a different, right? So have you considered those because they're not associated with the strong magnetic field?
Yes. So one thing this failed eruption flare does not cover is a CME without flare. That is, like you said, these large scale, flux rope with the filaments that's erupting. Okay, because the magnetic field is weak, the reconnection does not, eject lots of energy to create strong flare signals. But if the mass is large, okay, in the stellar CME detection method is actually better in the sense that it actually can absorb more. For example, in the H-alpha detection, it could absorb more H-alpha light. So you would get a clearer picture in that sense. but I don't know what fraction that is, because the current ones, most of them, what they observed is accompanied by the flare.
Well,
On the stars,
yeah.
they are mostly accompanied by, but on the sun, of course, yes. Okay, I have backup slides. So there are different detection mechanism. For example, one way to detect is that after the stellar CME, you have a loss of coronal mass. So the X-ray and the EUV luminosity would actually decrease below the baseline. And we see that for all the CMEs on the sun, and people have used that using XSM Newton and Chandra, looking at several stars, and they found about 20 cases with these kind of dimmings. So that's another way to detect CME.
Thank you. I think the torus instability, exploring it through the torus is really very, very interesting.
It's the expertise of my colleague. That's why I got into this. He's the one that actually studied this, for a long while.
Other questions? Okay, thanks, Xudong.
Thank you.